Suppose I have a control system, so that's a set of states and a path that starts at some initial state and starts traversing your space of states. And suppose I can control the direction of this path by modifying a few parameters. Now, local controllability means that I can achieve any state starting from the initial state. I can achieve any state in a neighborhood of the initial state by modifying the parameters in a convenient way. Now, suppose that there was a condition strong enough to guarantee local controllability, that I can achieve any state I want based on a convenient change in the initial parameters. Right? So now suppose that this same condition in a completely different field, stochastic PDEs, gave me the result that the solution to a few special stochastic PDEs actually have smooth probability densities. For stochastic PDEs, we know that if we solve a differential equation, that doesn't give us a solution, it gives us a distribution of solutions. And so the same condition here that implies local controllability of our control system implies that we have a smooth probability density for the solution of a few special stochastic PDEs. So two very strong results coming from one special condition. So what is this special condition? Well, we call it Hörmander's condition. And so what is Hörmander's condition? And I won't speak more of those applications that I just described. I'm going to say how Hörmander's condition actually came about, and that is when Hörmander was playing around with linear partial differential equations, and he came up with a very strong theorem, much like these two up here, about linear differential equations. He actually almost characterized the hypoellipticity of second-order linear differential equations of variable coefficients, right? So we know that we have, you might know a characterization of the constant coefficient linear differential equations, but as soon as we get to variable coefficients, things start to get very, very hard. And so a theorem that almost characterizes the hypoellipticity of such a large class of differential equations, which are the variable coefficient ones of second order, that's a very, very strong theorem. So let's start giving a few definitions. We have, so a vector field is an xj, an operator xj of first order. So first order given by these, the sum of these partial derivatives multiplied by these smooth real valued functions. This is what I call a vector field. Now define the sum of squares operator as, well, the sum of these squares, right? So a sum of squares of vector fields. And by squares, I mean just a composition of these vector fields. Now you can add, if you want, a first order term, which is just another vector field, and a zero order term, which is a smooth function. And now you can take it to be complex valued if you want. So again, what is this special Hörmander's condition? Well, I need a few more definitions. So we're going to define the commutation bracket now, which is, so the commutation bracket of x and y is going to be x composed with y minus y composed with x. You can also call this a Lie bracket. So this is also a smooth vector field because if you actually do this calculation, you'll see that the second order terms cancel out. So this is also a smooth vector field. And so therefore you can take, actually, if you have a set of vector fields xj, you can take the closure under the Lie algebra and then take the vector field over R generated by this closure under the Lie bracket, right? Okay, so this is what I call the Lie algebra. I'll denote it with this calligraphic G. And so the last definition that I need is the rank of G, the rank of the Lie algebra. So for that, I made this little comic book here to describe the rank. So in this first picture, we have the vector bundle that represents the Lie algebra, right? So each one of these little squares here is a vector field in the Lie algebra. Okay, so at number 2, we fix an x0. So we fix a point x0 on our domain and consider the fiber with base at x0. So this is the fiber. And now we project all of these vectors in the fiber to a single space. And so here are all the vectors in the fiber. And the dimension of this space is by definition the rank of our Lie algebra with respect to x0, of course. Okay, so now we have all of our definitions. And finally, this is what Hörmander's condition is, I'll give it in the context of Hörmander's theorem. So first of all, we suppose that the rank of G is constant. We do this so we don't have to, take the rank of G with respect to x0 all the time. So the rank of G is constant, and it's not equal to 0 because we don't want the degenerate case. And so Hörmander's theorem actually gives an equivalence. So a sum of squares is hypoelliptic. A sum of squares is an operator of that kind above. It's hypoelliptic if and only if its rank, or the rank of the Lie algebra generated by the vector fields that are in its definition, is n, where n is the dimension of our domain. So the sum of squares is hypoelliptic if we have a sort of maximality of the rank of the Lie algebra. Right, so this is actually Hörmander's condition. This maximality of the rank is Hörmander's condition that appears in those two fields that I stated earlier, which is control theory, stochastic PDEs, and many other fields. And so the reason I say the Hörmander's theorem nearly characterizes the hypoellipticity of all second-order operators is that we really don't need the sum of squares part up here, because hypoelliptic second-order operators are locally almost everywhere representable by sums of squares. So that's another motivation for, I guess, calling the theorem very strong and deep in a sense. So, okay, so this idea of Hörmander's condition for regularity or solvability, of a condition for regularity or solvability involving a span being maximal in some sense, or something being maximal in a sense, is not new, right? We have Frobenius' theorem, for example, on the solvability of systems of vector fields requires a condition called involutivity. And this condition of involutivity is also sort of a maximality condition, in fact, also involving the Lie algebra. And so another example now relating to regularity and not solvability is just this example of a very simple operator, which is just the partial derivative with respect to x, taken over maybe a subset, an open subset of R2. And it is not hypoelliptic simply because it's blind to the singularities in the y direction. So we can take a differential equation PDU equals f, and u can be very crazy in the y direction, but as long as it's smooth in the x direction, f will be smooth everywhere. Will be just C infinity. And so this equation clearly can't be hypoelliptic, and it's simply because it doesn't see the y direction, right? It requires more span in a sense. It needs to see more directions. Okay, so that's the motivation for Hörmander's condition, and also, I guess, the motivation of why Hörmander's theorem is very important. In the next video, I hope to prove Hörmander's theorem, or at least, because it has an immense proof, at least give the main arguments. And to save myself some time in the next video, I just want to talk about a very important lemma in the proof of Hörmander's theorem. So the lemma is Friedrich's lemma. And to state Friedrich's lemma, I'll need to define what a Friedrich mollifier is. And so the idea is, I guess, similar to a Dirac kernel, or a regularizing kernel in distribution theory. You take a chi test function and suppose that its integral is 1. Now you normalize it in this sense with respect to some epsilon, and you call this a Friedrich mollifier. You can also call a Friedrich mollifier the map that you get by taking the convolution with respect to a Friedrich mollifier. Okay, so U is a distribution. Now, so the Friedrich's lemma is the following. Consider a pseudo-differential operator of order m, where its amplitude is vanishing outside of some compact set. A pseudo-differential operator with amplitude vanishing outside of some compact set. Then we have two conclusions. The first one is that the commutator of this pseudo-differential operator with the Friedrich mollifier, for at least epsilon in some range over here, they form a bounded set of pseudo-differential operators of order m minus 1. Okay, so, but the most important conclusion is this kind of glorified approximation to the identity, which states that this, I guess you could either think of it as an approximation to the identity or as like a strong continuity theorem of this commutator with respect to epsilon. So the theorem states, or the lemma states that the commutator of the pseudo-differential operator and the Friedrich mollifier goes to 0 as epsilon goes to 0 in the space h of s minus m plus 1, where u is an h of s. Now this plus 1 is kind of surprising. Like, if this converged at all to 0, we would expect it to converge in h of s minus m because, well, simply the pseudo-differential operator of order m would reduce the regularity of u by m units in the Sobolev spaces. So this plus 1 here is kind of surprising. We have convergence in a stronger space, in a slightly more restricted space, right? So that's where the main surprise, I guess, of the lemma comes from. And I'm not sure if I'll be proving this in the next video, but certainly I'll give the main ideas behind the arguments in the proof of Hörmander's theorem. So that's all for today.